In this video, I'm going to describe how to combine two JSON feeds together using a dictionary in Visual Studio 2022. So I'm starting with a project where I have already consumed one JSON feed, and in this video I'm simply going to consume a second JSON feed using similar steps and then put them together with the dictionary. So we'll need to find some data that has a common key with the data that we already have, put it into QuickType, paste the generated code into Visual Studio, load the data into dictionary, and then iterate to find matches between the data. That's what I'll cover in this video. In a following video, I'm going to optimize this operation by using async await. First, why dictionary? And then we'll jump right into code. So we want dictionary because we want to consider big O notation. Big O notation discusses algorithm growth efficiency. So as we add more units to iterate over, how does the performance of the algorithm respond? And there's some well-known big O notations. O to the 1 means that as we add data, there is no growth in time to process, which is kind of the ultimate goal. That means you're ultimately scalable. O to the n means for every additional unit of data, we take one more unit of time to process. And O n squared means for every additional unit of data, it is exponential. Exponentially more to process, which we want to avoid because that would indicate exponential growth of the time it takes to process the item. So let's think about if we have two different data sets. We might think, well, I just load them both into arrays, and then I'll do a loop on the outer array and loop on the inner array until I find a match. But the problem is, assuming the data sets are roughly equal, this is O n squared. So 1,000 items on the outer loop times 1,000 items on the inner loop gives us 1 million operations. Now imagine if that's 10,000 times 10,000, that number is going to be much, much bigger. On the other hand, if we can have O to the n times O to the 1, we get a much slower growth rate, and that's what we have with the dictionary. So we might be looping over specimens in our case, but by using dictionary, we have direct access to an item based on a key, so it's O to the 1 performance. So if we have 1,000 specimens, and we could have 1 million different plants that we're matching them to, as long as those plants are part of a dictionary, we effectively get O to the n performance, or O to the n times O to the 1, which is about 1,000 operations, which is scalable. You know, that's something we can work with. So let's go ahead and take a look. Step number 1 is to find a data source. And in a previous video, I used a source of data, which are plants GPSed at the Cincinnati Zoo and Botanical Gardens, somewhere between 200 to 300 plants that are GPS there. We already have that on our project, and here's the JSON feed for that. What we want to add now is the ability to know which plants need water. And so specimens are one thing. Specimens are a specific plant at a specific location. So there are millions and millions and millions of redbud trees. Each one is a specimen. But if we're talking about all redbuds, then we'll talk about the plant called redbud or Cercis canadensis. So this new JSON feed we're going to consume is a list of plants, and I've filtered this down a little bit. There are about 6,000 unique genus species cultivar combinations in the plant places data feed. And by unique, I mean one represents a red oak, one represents a white oak, so on and so forth. What I've done here to minimize the data is I'm looking for only ones that are water tolerant. In other words, ones that are thirsty a lot. That way we can make our algorithm even more efficient. So from here, we'll simply follow the steps that I followed when I consumed the original feed. We're going to grab a sample of the data here. We could copy the entire thing, but that can get a bit unwieldy. So what we can do is just grab a sample. You notice we start with the square bracket, which indicates an array of data. And then we have curly, which indicates an object, and then a comma, and that continues until the very end where we end up with a closed square bracket. So we don't necessarily need everything in between, but we do need to maintain that same structure. So I'm going to start right about here, and I'm not going to copy that comma at the end, because I do still need to add that closed square bracket. So I put this together. I go to Json Viewer, and just make sure it's fit for purpose, and also that'll give me an opportunity to add that closed square bracket. I go to Viewer, and we see sure enough we have a fairly flat structure of data where all of our objects have the same attributes, but the attributes have a different value. So I will copy the text and put it into QuickType. Simply paste on the left, and I'm going to have it generate C#. Now careful here, let's give it a name instead of specimen, which is what I had before. We're going to call it plant. Generated namespace, my plant diary. I really want to keep that consistent because that's the same namespace I used for specimens. But there's one caveat here. QuickType generates a class called serialize and converter, and it's specific to this plant that we're trying to parse. And class names have to be unique within a namespace. And because I already have my specimen converter, it already has classes with these names. So I need to change the namespace just slightly. Maybe we can call it plant feed, something like that. As soon as I do that, I notice it changed here. Also, my name changed here. I'll Control-A, Control-C to copy. And now I'm going to go into my project and create a new file. We'll make this a class and we'll call it plant. And paste. Now, because this is the second JSON stream I'm consuming, I've already added the Newtonsoft package and several others that we're going to need. So I don't expect a whole lot of things I need to do the second time around that I did the first time around. And sure enough, I don't get any red lines, so we're in good shape. Now, I go to my index.cs.html. This is where I am currently consuming the existing data feed. So we want to add our new feed into here. Now, a couple of notes. Number one, there are a couple of refactorings I need to do to make this a bit more efficient. One I'm going to do right now, one I'm going to hold for a future video. Right now, we take a look at this onGet method, and it's getting a bit long. And a method should really just do one thing and do it well. To make this better, I'm going to highlight this, possibly everything but that last line, and then choose Edit and Refactor. And extract method. And you see it's actually pretty smart here because it knows to put this in a new method, make the return type of list of specimens, and then pass that to our CS.html file, the front end. So yeah, we're good here. We just need to give it a name. I'll call it get plant data. Just cleans things up. Next thing is that if you take a look at this, what happens is we call an async task, and then we wait for it to finish. Now, the nature of an asynchronous task is that we fire something, and then we hear back later. And ideally, while we're waiting to hear back later, we can do other things. Right now, we're not doing that. We're firing this asynchronous task and saying, okay, I'm going to wait until you're done. So we will improve that in a later video, and it's going to make a lot more sense as we're consuming two different feeds. But nonetheless, let's go ahead and start consuming our second feed of data, which is the plant data. We can reuse a lot of what we already have. For example, this client.getAsync comes from this HTTP client, which we can reuse. So I'll move down here. And into the getAsync, I'm going to pass the endpoint, or in other words, the URL that we saw just a moment ago in the browser that reflects my list of plants. Now, just like above, we'll say, okay, let's save that into a task, and let's wait. We can wait by asking for the result, and then we can save that into a local variable. Now, with this plant result, we can say, just as we have on line 46, result.content, read as string async. And that will give us back another task. Save that as a string. And then we can use the QuickType generated plant class in the from JSON method to take this string and create plant objects out of it and save that into a list. Alt enter here, introduce local variable. That will store the result of this to a list of plants. Remember earlier on when we were looking at QuickType, I mentioned that we want to use list instead of array. So you see here, and you see that's what it's giving us back, a list of plants. Also, while I'm here, I'll just confirm with you that this is the endpoint that I put in earlier, the endpoint that gives us this JSON result list of plants. So at this point, we have read in the data from over the internet, we've read it as a string, we've parsed the JSON. Now we need to put it in a dictionary so that we can see which specimens match up with these plants which love water. First, a dictionary uses the concept of a key, and that's what makes it efficient. And we know we need to find a data source with a common key with other data. If we look at our JSON feed, we'll see that each plant has a unique ID. And then if we look at the specimens, we see that the specimens have a foreign key back to that plant collection. So this is a common key. So we declare our dictionary, we declare the variable as the interface type. Now what does all of this mean? Well, when we declare a dictionary, first of all, I'm using the interface as a variable type, which follows along with the solid principles of software design. So specifically, dependency inversion principle is a good one, and lookup substitution to some degree. But nonetheless, we have to give it a data type for the key, which is that lookup key, and a data type for the value that will be returned when we look something up by that key. So long, because plant ID is a number, and then plant is the data type we're getting back, which is essentially an object. I'm saving this into a variable called water-loving plants, and then I simply invoke the dictionary constructor on the other end. Now I need to populate the dictionary with these newfound plants. So I simply use a for each loop. For each plant, oh man, I love this stuff. For each plant, and plants, what that means is we're iterating over the collection of plants, and each time we iterate, we're shaking hands with a different plant. The plant we're shaking hands with is going to be stored in this variable called plant. Now what's really neat is that Visual Studio here has figured out what I want to do. And it says, oh, I bet you want to add this to the water-loving plants collection. I'm like, yeah. So I just tab to accept, and there we go. It did a nice code completion for me. And now we have a dictionary populated with plants. Now, of course, the more plants we have, the bigger this collection is going to be, and there's some time to load the collection. But after that, it uses an algorithm to find the key in memory, so really the size of that dictionary doesn't matter. It still gives us that magic O to the 1 performance, because it's just doing simple division to find where a specific key lives within this collection. Next, we can find out which specimens like water, and we can add them to a collection. What's going on here? Well, notice I'm using a for each loop to iterate over the entire collection of specimens. Once again, with the for each loop, what I'm doing is I'm dealing with the collection. I'm shaking hands with each item individually on each iteration. So each time I shake hands with an item, I ask it for its plant ID. And then I say water-loving-plants.contains key specimen.plant ID. Remember, water-loving plants is a dictionary. So it's simply looking for this key using that algorithm to see if the dictionary contains that, which gives it relatively direct access to that location. It's either there or it's not. So this is effectively an O to the 1 operation, where the enclosing loop is an O to the N operation because I have to shake hands with every specimen. So you see, shaking hands with everything, O to the N, but direct access, O to the 1, much more efficient than shaking hands with all the specimens and then having each of those specimens shake hands with all the plants. Finally, that's going to add to a new collection I just made called Water-Loving Specimens. And we will return that here. Now, we know there are about 300 plants GPS'd at the Cincinnati Zoo and Botanical Gardens, and you see this list that we have is much smaller than we had before. The reason is we're just looking at those water plants. So I've set a few breakpoints here so we can watch it in a bit more detail and at our own pace. We see the page begins to load, and we're in the get data call. So I'll just do F10 a few times as we walk over some things that we did before, including getting those specimens and parsing them. So this we've seen before, validate the schema, nothing crazy going on here. Okay, specimens are all good. Now we're getting the plant data, and we're getting those plants from strings now to objects of type plant and a list of plants. Now we're iterating over that list of plants and adding it to the dictionary. So every plant will get added to the dictionary. It'll take a while, so I'll just choose F5 to tell it to continue to the next breakpoint. Next breakpoint is creating the water-loving specimens. Now watch this one, because remember we're shaking hand with every specimen. And then as we do it, we're saying, oh, specimen, you have a foreign key back to that plant concept. So let's look at that foreign key and see if that exists in the water-loving plants collection, which is that smaller collection of only plants that like water. And you see the vast majority don't, because if you notice that line 80 is not getting hit very often. So once again, I'm going to switch from doing F10 to F5, which will say run till the next breakpoint. When I do that, we see that that breakpoint is indeed getting hit, although it's skipping over the ones, as I choose F5, it's skipping over the ones that don't get hit. So we see it is getting hit to some degree. So I'm going to take off that breakpoint. I'm going to choose F5 and take a look. We have our consolidated list. So in this video, we've seen how to consume a second JSON source using that same HTTP client and the quick type that we've used before, load that into a dictionary, and then use a common key to go from what would be exponential growth of an algorithm to simply linear growth, or O to the n growth, where every additional specimen we have requires just one more step of processing, instead of every additional specimen we have needing to shake hands with every single plant we have. So this is an efficient, scalable way to do things because it can handle various amounts of growth. I've worked full-time in retail for quite a while. And one trick about retail is that demand is very lumpy. As you get holidays and you get special releases and launches and things, and you can have an IT infrastructure that's like this and then suddenly has a peak demand like that. And scalability is really a good way to handle that. So I hope you found this video helpful and maybe thought of some new ways to read data and combine it. In the next video, we're going to make this even more efficient because we're going to be able to read those two JSON data streams simultaneously instead of reading one, waiting for it to complete, doing some work, reading another, waiting for it to complete, and doing some work. That also is a very major task these days, or very major concept, because we think about the mobile programming environment. A lot of times we make a call to one API that's calling many other downstream APIs. It needs to call them asynchronously, assemble the result, and send it back to the mobile client. So all of these very good skills that I'm happy to share with you, and I hope you enjoyed watching. As always, I look forward to seeing your comments. Thank you.